Okay, so let's talk bending. All right, so yeah, previously we'd been talking about indeterminate problems. We discussed axial and torsion loading, and now we're basically going to be doing the same for bending. But first, we're going to talk kind of what bending is. So, uh, quick reminder of the sign convention that we used when we were basically going about figuring out what our, doing our shear and bending moment diagrams. Uh, so again, if it is something that is going to be causing a moment that kind of causes a little causes it to form like a smiley face, then it'll be a positive moment. If it's going to be uh, causing a moment that causes a frowny face, that'll be a negative moment. And basically, what the reason that that was chosen is because as we move left, the as we go this way, uh, this if the moment is positive, then that means that the slope is increasing. Not doesn't necessarily mean that it has a positive slope, but whatever the slope happens to be, it's getting bigger when this moment is positive. So it has a for example, at this end, we're starting off with a negative slope, but it's steadily increasing and continues to get bigger until it gets to this end. Whereas if we have a negative moment, we could start with a positive slope, and it'll be decreasing as it moves along. So based upon that, if you kind of look at the way this deforms, what's going to happen is if we look at lines kind of drawn across across the beam here, and I'll kind of go back to here, you'll see that kind of right here, along here, the lines are getting smaller. Whereas, so that's on the inside of the curve. Whereas on the outside of the curve, they're going to have to get bigger. So it spreads out on the outside, squeezes in on the inside, and then there's going to be what we call a neutral axis somewhere in the middle where the line length stays the same. So here that's denoted here. We have some neutral axis here, and then basically above that point, so we're talking a positive moment here. So positive moment, that means that in this configuration, at the top here, these, this, these little segments here, they need to get squished in. So they're going to have a negative strain and a negative stress induced in order to cause that negative strain. So they're getting squished when you bend it up, they're getting squished together at the top, and they're getting pulled apart at the bottom. So that's when we have a positive moment. If we have a negative moment, the opposite happens. We're getting tension on the top, and we're getting compression on the bottom. So the strain, you're gonna have the strain kind of varying from some point. So the neutral axis is going to happen at the centroid of the cross section. That's the way it works. So whatever the centroid of this cross section here is, that's going to be the neutral axis here. So that's basically saying that, if we take this thing and kind of look at a cross section like this, whatever line is parallel with this, when we bend it, that line stays the same length. So that's yeah. The neutral axis is located at at the same y height as the centroid, and then the strain varies linearly from that. So you're going to get zero strain in either direction here, and then as you go up, you're going to get uh, you're going to get uh, more strain, more negative strain, because again we're bending it like this when it's a positive moment. So we're going to get more negative strain as we move upwards. More. Oh, come on. Oh, come on. Didn't mean to do that. Anyways, yeah, more negative strains we get as we get further away from the neutral axis in the positive y direction. More positive strain when we get further away in the negative y direction. So if the strain varies linearly from the centroid, then the stress does too. So if we take a look at a tiny little cube at some point here, we've got a little differential area here. Again, that stress is varying linearly from the centroid. And so that tiny little cube has a stress that is exerting a force, and that force, when we take a moment about this axis, that force is going to exert, that little force is going to exert a moment about that. So that'll be equal to the stress of that point times the area, which gives us our force, times the y distance between those segments there. So this, we're able to find our kind of our tiny little differential amount of moment. That's going to be equal to negative, again, because of our sign convention, y times our stress. Again, it's that stress is on this face, so the stress in the x-axis, so coming out of the page here, times our dA. So we know that. So if we want to figure out what the total moment is, the total internal moment, that's just going to be us integrating that over the entire area. So basically, we need to find out what our stress there is. So again, that's going to be based upon our strain and our Young's modulus, because we're assuming we're in the linear region here. So the stress induced is still directly proportional to the strain. Or conversely, the strain that happens is directly proportional. It is directly proportional to the stress that you put on the object in order to cause that strain. So, figuring out what that strain is. Okay, so if we have a look at at a segment of a beam that's subjected to uniform bending, we get basically a portion that's curved into an arc of a circle. So this is a segment here. It has a radius of curvature, and you're going to get a certain segment here where the length is unchanged. So along the neutral axis, you're going to get a certain length there that is the same as the original length of the object. So that distance, that original length, once it's curved, that's just going to be rho. Rho is kind of defined as the radius of curvature times whatever angle we're kind of what sort of angle gets formed over that segment. And then the other lengths, they're going to vary. So they're going to be varying based upon the radius of curvature and upon the y distance. So again, if we look at the segment JK here, so that's at this is this one here at some distance y from the neutral axis. its length post deformation, that's just going to be based upon the arc there, the angle there, again in radians, times the distance between the center of curvature here and wherever we're going. So that'll be rho minus y. So if we increase y, if we move up from the neutral axis, that distance gets smaller, so the length of the line also gets smaller. So again, since we know that the original length was L, that deformation is going to be equal to whatever we just calculated minus L. Putting it in terms of these terms, we can get our new length, rho minus y times theta, and then minus the original length, which is rho theta, gives us a delta of minus y theta. Then we've got that, so we can calculate our strain. So our strain is just going to be the elongation divided by the original length. So our elongation here divided by the original length L, our rho theta. The thetas cancel out, and we're left with just a negative y divided by rho. So basically what we can do is we can plug. So we found out what our strain is. We can go. That's what we're trying to figure out here. So we can plug that into this equation here, and we can basically find how the moment affects the basically the relationship between the moment, the Young's modulus, the radius of curvature, and this thing here. So this term here, the integral of y squared dA. So that's a function of the geometry. So specifically, it is a function of the geometry of the cross section only. So I'm going to scroll back a little bit here. So if we're looking at this thing here, then if we take each little small area thing, multiply it by the y value squared. So the distance from the neutral axis to here, and then add all those up over the entire area. So integrate, then that'll give us that integral there. So again, we typically represent that as Iz, and that is basically a number that represents the ability for a particular beam cross-section to resist bending. So what it's called, so that is often referred to as the moment of inertia, or sometimes the second moment of area, depending upon who you're talking to. Either one works. You're typically going to find, like, if you don't even want to look them up on Wikipedia, I'm pretty sure it's under second moment of area. But anyways, so yeah, that relates the relationship between what sort of bending moment you apply, the material properties, that thing, and the radius of curvature. So if you subject a beam to a particular bending moment, if you have a large Iz, then you're going to get a larger radius of curvature, which means that the curvature is less. So if you have a large radius of curvature, it's not curving as much. Whereas if you have a smaller radius of curvature, then it's curving a lot. And obviously, similarly, if you have a larger Young's modulus, if your material is stiffer, then you're also going to get a larger radius of curvature, which means you're going to have less curvature. As for what sort of stresses get induced, we can go back to the kind of the formula that we already solved for. Sorry, one of the previous steps in the that we looked at here. Kind of just plug that what we solved for I into here. So the solving for the stress, it is directly proportional to the moment. A large moment induces a large stress. I don't think that should be surprising to anyone. It is inversely proportional to the I. So having a large I means that you have a smaller stress level induced. And it is directly proportional to the distance from the neutral axis to the place you're looking at. So again, the maximum stresses always happen at the top and at the bottom, so the maximum magnitudes. Again, if you have a positive moment, it's going to be compressive at the top and then tensile at the bottom. And then if you have a negative moment, obviously the opposite happens. If you have a negative moment, then you're starting to push on this and pull here in order to induce those forces. As for the eyes, it's generally not all that efficient use of your time to go ahead and be doing that integral every time when oftentimes we're working with geometric shapes that are fairly uniform, and we can just go ahead and look up what that is on a table. So just keeping in mind that the IZ would be telling us what its ability to resist rotation about the z-axis, and the y would be telling us its ability to resist rotation about the y-axis. So again, we're using y and z in this configuration because we've been looking at beams, and generally speaking, when we're talking with beams, we're using the x-axis as increasing along the length of the beam, and then y stays vertical. So then z will be will be the depth of the beam. So if we're looking at the cross section, it'll be looking like this, and then the x-axis will be coming in and out of the page. That's one thing to keep in mind, because oftentimes when you go to look up I tables, they're often, and this includes in your textbook in the Hibblers, they're often oriented. So this is the x-axis, and this is the y-axis. So you need to just kind of convert that mentally to make sure that you're getting the right set of values here, basically. So yeah. So about the z-axis, it's 1/12 base times height to the third. So the unit should always be some unit of length to the fourth. Whether it be inches or millimeters or meters if you want really small numbers. Yeah, so some unit of length to the fourth. So basically, having a larger base does help resist rotation, but having to some degree, but having it taller resists more. So if we kind of say, I got this ruler here, it's relatively wide, but it's not all that. If we look at the cross, if you look at the cross section, its base is relatively wide. Its height is not very high at all, so it is not able to resist rotation too much when it's about this axis. If I rotate this, however, if I rotate it so it's like this, then suddenly our height is fairly big, and our base and our base is relatively small. So and when I try to rotate it about this axis, I can't. I can barely move it. So it's the same object. It's the same object. The cross-sectional area is the same, but the eye about this axis, eye about this axis versus the eye about this axis, drastically different. So the orientation of your beam matters quite a bit. So that's for a rectangle. Here's the calculation that you'd use for a triangle. Again, about this axis. Semicircular area, about this axis for Z, about this axis for Y. They're the same thing. And also for a circular area. They're obviously it's symmetrical, so that is obviously the same thing. But just 1/4 pi times r to the fourth. And again, you're always going to end up with some sort of length unit to the power of 4 for your I value. And yeah, that's it for now.